Okay. Oh, so you're there. I was waiting for you to come. Okay. So let's continue with the GCC source localization method. What exactly it says, it's just from this, the title, it's clear that we are going to find the cross correlation between the data. So here we assume just one pair of microphones. So microphone 1 and microphone 2, as we already had in the previous slide. So just assume this kind of localization strategy. We have just two microphones, M1 and M2, and there is a source far enough to have the far field assumption correctly. So we have far field and we have near field. Far field assumes that the source is far enough from the microphone array, from the sensors, such that the wavefront is coming parallel to the array. When it's near field, then it's mostly, it's in a radius form that comes to the array. So it's the close distance microphone, and the close distance source to the microphone. And it's a bit different, but here we just consider the case that the source is far enough from the microphone set, the same as what we have in the radar. And the wave front is actually coming in parallel to the array. So this is the strategy. But the point is that here we're talking about just two microphones. It will be possible to generalize that to any number of the microphones. Any number of the microphones. But the GCC function is applied to pairs. So depending on how many microphones you have, then you have the GCC functions to calculate for every pair of the microphones. Did you notice it? GCC function on every pair, not just one time. So if you have n microphones, how many GCCs you need? How many GCC functions you need to calculate? N times n minus 1 over 2. That's the number of the GCC functions, number of the GCC functions you have to calculate. Okay. Some people look at me, every statement is a kind of, problem in the exam. So, okay. It might be, actually, because the statements are more important than the equations. You can find these equations everywhere, but the statements and how to explain it is more important. So, let's talk about the GCC function. We already talked about autocorrelation and cross-correlation. So everybody knows that. What is autocorrelation? What is cross-correlation? Assuming that the signal which is coming to the one microphone and the signal which is coming to the second microphone is different. Assuming that these are two different signals, while in the sense they are just one signal, but propagating two different paths. That's the difference, but we can assume in mathematical format that there are two different signals coming to two different microphones. Then we know that the correlation function, autocorrelation or cross-correlation, which here we assume is a cross-correlation between x1 and x2, signal in the microphone 1 and signal in the microphone 2, it's in time, but it has a duality in the frequency domain, okay, which was called, so we had autocorrelation, and the Fourier transform of autocorrelation was power spectrum. And if for different two signals, it was cross power spectrum. For one signal, it was auto power spectrum of the signal. But we know that the autocorrelation and power spectrum, they are dual, one in time domain, the other one in frequency domain. So in general, the autocorrelation, this generalized cross correlation, can be written as inverse Fourier of x1 and x2 in the Fourier domain. So it's the inverse Fourier of this function, x1, x2 conjugate. But we will give it a weight function. psi 1, 2. Psi, a weight function between the pair 1 and 2. It's a weight function. It's very important to use it. And that's the kernel, just the kernel which transforms from the Fourier domain to the time domain, that's all. If the signal is assumed to be stationary, we know that autocorrelation only depends on the time difference. If the signal is stationary, the cross correlation or the autocorrelation just depends on the delay between these two signals. Okay? So, the cross correlation between signal 1 and 2, which assumes to be stationary, it means that only depends on the delay between these two, the time delay between these two signals, which is called tau, is actually respecting this equation, which is the inverse Fourier of x1, x2 conjugate together with this weight. So this weight is something we added to the Fourier transform. So it means that for every frequency we give different weights. But there is the best of the weights that has been figured out so far is called the phase transform or FAT weight psi 1, 2, which is just a normalization over x1, x2's conjugate, the absolute value of that. So in general what it does is just reducing the sensitivity for those frequency bins which are which the entire cross correlation is more sensitive. So it unifies the sensitivity over all the frequencies. That's what exactly this psi 1, 2 does. But the point is that what we have already, we have the time difference. The time is the fraction of the distance over the speed. Okay? It's from the high school or elementary school physics. So the time is the ratio of distance over speed. This is the speed of sound. But this is the point of the source, the location of the source, which can be showed by, so the spherical coordinate, it can have a radius, which is the distance, the azimuth, and elevation. So azimuth is theta, and elevation angle, which is phi, and r is the distance. So that's the point source. The difference between the point from microphone I and the point from microphone J, so we have distance from point to microphone I and point to microphone J. Difference between these two is that part of the small difference that the wave was about to propagate from one microphone to another. So that's the distance. The difference of the distances from the source to these two microphones over the speed of sound, which gives us this difference in the time, presumably for these two microphones. So the time delay or time difference between these two microphones for the same point source is represented by this equation. It's very simple. If we can calculate the cross correlation between the signal 1 and 2, the microphone, using the first equation, then giving those weights and knowing the position relation, the position and the position of the source microphones and the time delay, then we know that the choice of time delay of arrival is the one which maximizes this autocorrelation function. So the tau which maximizes that function is what we need. The optimal value for the tau is the one which maximizes the autocorrelation function, the cross correlation function. That's the tau we are looking for. If we can get the tau here, you put the tau here, you know the speed of sound, you know the position of MI and MJ is the microphone array that you're using. So you know already the position of the microphones. It's already fixed. Then you can get P. And that's the story of GCC. GCC based localization. So you get the TDOA, and based on the TDOA, you put it here and get the P. That's all. Now, if you have more pairs, what happens? The only difference is that you have this GCC function for several pairs, 1 and 2, 1 and 3, 1 and 4, 2 and 3, 2 and 4, and so on and so forth. So, combination of the pairs for the GCC functions. You look for the tau, which on average maximizes all of them. So you can take the average of these GCC functions, the average over all these GCC functions. The tau that maximizes that average is the one that you need. So it's like the intercept of all of these functions in one point. If you can find one point, that maximizes this average over the entire GCC functions, that intercept point is the tau that you're looking for. You find it, you put it here, you get the P. Because you already know MI and MJ for every I and J. You know that, it's an array, you know the positions, you will get it. But it turns out, in reality, and usually for the case of enclosure, like a room, like big halls, that because of reverberation and noise, we get several different peaks in that, the cost function, in that tau, which we're supposed to look for and to find it. We get several peaks, and it's very hard for the high reverberant environment to specify one of these peaks to the exact time delay of arrival. Because of so many peaks that we get, for example, here it's for the low reverberation environment, but you get several peaks, and one of them is because of the direct path, and the other because of the reflections. So it might happen in a case that these peaks are almost in the same level, so you don't know which of them to pick, and any of them is different. Here you have 19 milliseconds, for example. Here you have 20 milliseconds. Here you have 20 point something milliseconds. And here you have 28 milliseconds. And any of them means the location of the source is different from the other one. And 28 milliseconds for the speed of 343 meters per second, it means a lot. So, there are methods how to deal with it, using the Kalman filters, particle filters, and so on. I don't want to go through that. It's a lot of theory. And I just gave you the flavor of GCC function for localization. If you want to understand how exactly to do it in practice, you have to follow me until this point and then continue by yourself to the end of other practical methods. What SRP does, in a sense, which makes a difference from DOA estimation, from GCC estimation method, is that it says, assuming that we have Q number of the pairs, it's a pair. So, well, I already explained the essence of SRP. So, SRP is just making the beamformer to look for entire space and then finding the place which gives you the higher energy. And that higher energy can come from the accumulation of these cross-correlation functions, because you know that cross-correlation gives you the variance. Variance is energy. So the R of 0, when tau is 0, Rxx 0 is the variance of signal. What is the variance? The variance is the energy of the signal. Okay? So the SRP method says that SRP at that point is actually an average over all the cross-correlation functions for different pairs, and the time delay associated to those pairs. So we know that pairs, and we get the time delay for every pair, the cross-correlation function for all of them. We accumulate all the cross-correlation functions, which is nothing but the energies. We accumulate over all the entire energies. The value of tau, the value of location, which maximizes this energy is the place. So there is a place that has the maximum energy. That place, P, is the one we're looking for. So you see that how it's related to the GCC method or TDOA method. We don't want to go through the SRP method until after the beamformer. You can just go through that. If we ask anything about localization methods, just the first one is our intention. And you know that these are, for example, n microphones in circular array. If you have n microphones, then how many number of the GCC functions you have to calculate? N times n minus 1 over 2. TDOA method, the first one, in the previous page, the first one, is the one that you can use it in real time, because it's just calculation of a simple function. And if the number of the microphones are not too much, then n times n minus 1 over 2 is not too much. You can calculate it in real time. And that maximization problem is just simple. Put a tau, it maximize that. A linear maximizer, you can just find it. So you can use it in real time. But the resistance response power is something that depends on the granularity of the environment, how you make the grids for that environment, 3D environment. If the grids are so big, resolution is not good. But if you want to get a good point source, then it's costly, and it's better to forget about that in real time. Okay. Here in this slide, what I'm trying to say is that, so I just broke down everything. In this slide, what I'm trying to say is that we want to find the location of the source. But what happens if the source is not talking? How do you want to point to the source, find it? So the point is that the localization for the acoustic source just happens when the source is active. When the source is active. Voice activity detector is a system prevalently used in signal processing for many cases. And it means that apply all those scenarios I talked about only when the source is active. So the entire process is activated using this actuator. If this says that this frame contains a source, then do the process. Otherwise, it makes no sense. So what happens if you use the voice activity detector and it indicates that there is no source in this frame, and then for 10 consecutive frames there is no source, then I don't know, 20 frames later, then source starts to talk again. If the source starts to move, then the location will be changed. So you need to do the process from the beginning. But those sophisticated methods of Kalman filter, particle filter, and so on, which I explained a few minutes ago, are the techniques that talk about the dynamics of the system. Because you know that there's a person who talks in the environment, and probably the speed of movement of such a person is not more than the speed of sound. He's just walking, probably, and he will just walk, I don't know, maximum case 5 meters per second, if he's like a jaguar. So it's not that much. So you can set up a dynamic system, like the one that you use normally in Kalman filters, I think we can have some time during the DSP lecture to talk about the Kalman filter. So it means that there is a dynamicity for the system, for the speaker. And then using the Kalman filter, you can just do the entire process in a recursive manner. Recursively you can say that, okay, the point, the source at time t was here. So it wouldn't be, too much farther from that point that we already calculated. But if the time of the silence that this voice activity detector gives us is too much, then you should look around in a much larger circle, in a much larger environment around the previous point. So from all of those points which can respect the optimization problem, you are giving weight to the points which are closer to the previous estimation. Did you get it? At time t0, you figure out that the point is somewhere here. For example, here is this source located at time 0. Then it takes a while. If it's exactly the next frame, then because you know that the movement of such a guy will not be like a light or like a speed of sound, so you know that maximum area that you should look around is such a, 1 meter circle or 1 meter sphere. So if based on those reverberation and noise you get several peaks, which of those peaks is the one which satisfies your equation, is the one which locates inside this circle, because the movement shouldn't be more than that. And many other peaks should be thrown away. But what happens if, for example, for 2 seconds, for 10 seconds, voice activity detector tells you that there's no activation of the source? Then it means that you need to have a much bigger circle, because probably the source has moved around much higher. That's the uncertainty of the location that you might face with. It was just for your information. So that's voice activity detector application that we need actually to have it. When you have multiple sensors, 2 different scenarios might arise. One of them is called beamforming, which means that there is a noun geometry for the array assumed to be. So we have a noun geometry. The array positions are already noun. M1 to Mn, everything is noun, exactly the position. But there is also another scenario which is called source separation or blind source separation, which blind is not that much blind because we use a lot of priors. But the subject is called in general blind source separation or BSS, and this is called beamforming. In blind source separation, we don't need to have and assume a geometry for the array. So arrays can be distributed without any noun geometry. But what we do is we try to estimate the mixing metrics. So the signals are already mixed in these microphones. We want to find a demixing filter. But how to understand this demixing filter, how to make it, based on some information theory stuff. I will talk about the BSS and ICA as the generalization of PCA actually. So you assume a demixing filter in the initial point, you get the signals in the output, then you try to correct this filter based on the prior knowledge that you have. So you need to have some kind of knowledge, the prior knowledge. So it's actually, depending on the prior which you're using, is a supervised algorithm. And these are in general in the content under the subject and under the umbrella of machine learning methods. So blind source separation methods like ICA, non-negative matrix factorization stuff, any type of factorization. These are all methods prevalent in machine learning. I'll talk about this just briefly in one lecture. So that's the story of BSS. And for the beamforming, you know the geometry between any two pairs and for the entire microphones. And you get the signals, and you have the difference of arrival for any of these microphones based on the distance from the microphone to that source and this theta angle. What you try to do is first localize the signal. How? Using the previous algorithm, TDOA, GCC. So you localize and you figure out what is the point source. Don't forget, we just get the theta and phi. We're not talking about r. The distance is not possible to get it because there is a large ambiguity in the distance. It comes from from this fact that we don't know what kind of intensity the speaker started to talk. That's always unknown. That's why we don't know actually what is exactly the R or the distance. Because the guy might stand close to the microphone array but speak very slowly, or he might be far away and speak very loudly, the one I'm doing now. So that's why the distance is always ambiguous. But we can talk about the azimuth and the elevation. Okay? So, in the few slides remained, I will cover the beamforming part, but the BSS will come after one of the lectures. I'll just briefly talk about ICA and some other methods. What is beamforming? We have two types of beamformings actually. Receive beamforming and transmit beamforming. But in the literature for the acoustics, for normally speech localization, inherently when we say beamforming is the receive beamforming. But in general, in the avionic, in radar systems, we can have both. What are the applications of beamforming? In general, beamforming, the receive beamforming is that you want your array to steer just toward your desired speaker and not anywhere else. So you have speakers here and here. You want to just listen to this speaker and ignore the other one. It means you want to shape a beam or a gain pattern, which this gain pattern steers toward this speaker and gives almost zero gain toward any other direction, including this speaker. That's the receive beamformer. For the transmit beamforming, we want to send a signal toward a kind of beam pattern. And it's very useful. There was a very nice application. Assume there is a supermarket, a very huge supermarket like the Walmart in the US. You get close to any of these chambers or these stands, the kind of goods there, and you might know the information about that, or probably you don't. So either there should be a person there to speak about and advertise that kind of goods there. For example, I don't know, detergent, that's a kind of cosmetics. You might know that, or you might not be aware of that. So either there should be a person, or there is a device, probably that device is hung over somewhere, and that just based on your location, which is getting close to one of these stands, then you hear some voice talking about that part of the goods that are existing there. That's an example of the transmit beamformer. Or there's an airplane moving, just flying over villages, but just wants to send the information to one village and not to the others. Specific information to be sent just to one place. Beforehand, it was just broadcasted, so everyone could get the information, but based on the coding information, they could decode it or they couldn't. But in general, everybody could get the information. But it would be possible using the transmit beamformer to just send the information to the place you want and not to the others. These are examples of the beamformers. Here we mean this as a beamformer. Okay. There are two general types of the beamformers. One is the beamformer which depends only on the geometry. Only on the geometry. Geometry of the array and the environment. And doesn't care about the data itself. What is the data? I don't care. I just care about the locations and the geometry, the physics of how it's propagated. But I don't care about the data. That kind of the beamformer is called fixed beamformer or data independent beamformer. And there are two famous methods that are contained in this category, in this classification of beamformers. One is called delay and sum beamformer. I'll talk about it just a few, maybe the next slides. The other one is super directive beamformer. Super directivity means to have the maximum directivity based on a measure, based on a kind of measure, we will talk about that measure, to have the maximum directivity toward one location. So, but we should understand that we are just talking about data independence, so it shouldn't depend on data itself. X shouldn't be important that much. And for the data dependent beamformers, we have different types, but we don't talk about that. Adaptive beamformers or data dependent beamformers like LCMV and GSC structure and so on. We don't talk about that. It's going much further into the theory. What is the story of super directive? A very simple statement in this slide. Super directivity means that there is a linear structure. Maybe it's better to just write down a few let me start from here. So in general, you have data in the microphone. It's called X. Let's assume that X is the clean signal. So this is the clean signal. Clean signal is the one that you want to get it. After doing the process, you want to get this clean signal. What is it? So there should be a kind of function applied over this clean signal and then gives you the signal in the microphone. So what you get in the microphone is not the clean signal, but this clean signal has passed through a nonlinear function probably and then recorded by the microphone. So the microphone gets the signal, which is nonlinearly, some nonlinear function is applied over there. And probably there's a noise also added. There's a noise, additive noise from the environment, the background, or the noise of the microphones, internal noise, which gives you this equation. That's the model of the data in general. So that's the signal from the microphone. Observed signal. In machine learning, you say that this is the observed variable. And X is unknown. There's a latent variable. We don't know that. In many machine learning methods, we're looking for linear functions. So if we can somehow linearize the equations and get the answer from the linearized equation, that's the best we can get. Like the linear regression. Linear regression assumes that this data, there is a linear fit of the linear function as the regressor of the data. So here we assume that this function is linear from this point forward. When it's linear, then based on the information we got from the previous lectures, you can assume that this data, the microphone, which is a vector of data, Z1 to Zm, number of the microphones. So we denoted by this vector Z. This was the vector, doesn't matter. That's a transform for a matrix of H applied to the X data. This X data is X1 to Xn based on number of the sources that you can have, which for our case we can assume just there is one source, so it can be instead of a vector we can just assume a scalar value for the frame, for that frame. So we can ignore this plus a noise. A noise is vector, the same as this one. Noise at the microphones. So at microphone 1, at microphone n. That's the general description. Is that there? So, if we can assume that there's a linear function governing this model, this is the general representation of that. Z in the microphones is a linear function over the signal in the sources, in clean sources, plus added noise, some added noise. That's the general model. Now, what we want is, we want to apply gain over these microphones, and we can assume that this gain is W. So W means W1, or a weight function. W1, Wn. We need to apply W over the signal in the microphones such that it gives us the good estimation of the source. That's what we want. So, what is this weight? That's the question. The question of beamforming is, what is this weight function? Okay? Here, there's a point. So, this is called the mixing matrix. How the signals or the sources, or how one source is passed through different channels to be recorded in the microphones, and then some noise be added to it. So this is a matrix, or in one, or it can be a vector, depending on the environments, that shows how the signal goes through different channels to be recorded in the microphones. So this is unknown. X, the source, is also unknown. And noise is in general unknown, but you can just assume a kind of variance for the noise that can be calculated in specific conditions. So what kind of equation is that? That everything on the right-hand side is unknown. You get just the first part, the left-hand side, and you want to estimate everything else. And in more than 99%, we can assume it and we can solve it. So that's called inverse problem. And these inverse problems are, in general, for the mathematicians, are the hardest problems everybody can face with, because different conditions happen, and based on different conditions, different types of solutions you have to look for. So we need to start from one point. We need to start from a kind of prior, a kind of information. And the information that normally in the beamformers, especially in the fixed beamformer or data independent beamformers, happen is that we assume something about this and we try to get this. So we try to mitigate the difficulty of the problem by having some kind of assumptions about this one to be able to get something about this one. And the assumption that we make for this is that we approximate H with a vector which is called array manifold vector. So H is assumed to be known, and we call it as V or whatever else. In that place is assumed with this H. In this slide is assumed to be H. Doesn't matter. You can have H or V. Normally it's in the literature is shown by the V, and it's called array manifold vector. And what is this array manifold vector? What it says, it's actually based on the location that you already find. You can find it with the TDOA method. So array manifold vector in the frequency domain is nothing but this one. E j omega tau 1 E j omega tau m. So if you know the location of the source, because you know the location of the microphones, you can easily calculate this tau 1 up to tau m. How? Tau I is an inner product. So assuming that the direction is, normally what you do is, for example, for circular array, you assume that the center of the circulation is the center of the, orientation, whatever you do. Origin, that's the origin. So you have a vector A, cosine of theta, sine of phi, sine of theta, sine of phi, and cosine of phi. Transpose, because normally we show every vector with the column. And these are the azimuth and elevations. So that's the direction of the source with respect to the origin. That's A. If you know this A, then tau I is nothing but the inner product between A, which is A transpose, mi over the speed of sound, which is called c. So you can, by this equation, you can simply get every tau value or the time delay value between the source and that microphone, any of these microphones in the array. Just if you know the mi for this one, m1, m2, and so on. The inner product between this A and this vector of mi, it has for itself a vector. For example, the vector between this and origin is this one. So projection, inner product is a projection. So the inner product between this and this, which represents a kind of this angle, and the amount of projection which gives you, if you know this angle, the amount of projection which gives you this distance over the speed gives you the time delay. That's a relative time delay because we can assume we don't know the R, but we normalize everything for one of, for example, we assume that this is the first microphone, just as an assumption, and this is the second, and so on. We make this one to be 1, so normalize it to be 1, and we calculate the rest as a relative tau with respect to the first one. And we get this array manifold vector, V. Then, if you know the V, you have somehow given this value. Now the point is how to calculate X is very simple. You just say that I need W as a vector when applied to Z, give you this X. But I want an estimation which is unbiased and minimum variance. Which is called in general minimum variance unbiased estimator, MVUE, in the estimation theory. MVUE is the best linear estimator that you might have. The best linear estimator is minimum variance unbiased estimator. What do you mean by unbiased? It means that expectation of the estimation should be the same as expectation of X. And you know that this estimation is nothing but this. So let's write it here. So we put W transpose, we take it out of the, I take it out of the estimation. And we know X is W transpose Z. So, and we can assume that Z is HX. So W transpose H, which is assumed by V. So W transpose V expectation of X equals to expectation of X. So I just took out everything. It was W transpose Z. I wrote Z as HX, which H is already V transpose. And when that one is transposed, so it means a Vx. So that's the unbiased condition. It means that this will be cancelled by this one, and W transpose V should be 1. That's W transpose or conjugate V, it should be 1. A here, it plays the role of V, which is assumed to have dependency on the azimuth. And V here, we see that V depends on tau m, and tau just depends on the azimuth or elevation. Depends on whether you want to keep the azimuth fixed or the other one fixed, or both of them variable. But in general, that's how it depends on. So that's why the condition, one of the constraint is actually written as this form. But I will give you the intuition also in a very simple statement. And if you try how to make it minimum variance, how to make it as a minimum variance. So the minimum variance means that the variance of X hat, or your estimation, should be minimized. And if you just replace this with this, doing the simplification, finally what you get is W transpose. So expectation of, let's write down as R Z W. So I'm coming to this slide, but I'll be back again because I wrote this equations here. So assuming that V plays the role of H in that equation, and S is the source, and N is the noise, finally you get W transpose or Hermitian in the general sense. When it's a complexity, you can write it down as Hermitian. And this is the covariance matrix. But the point is that for the super-directed beamformer, the covariance matrix of the signal in the microphones, we assume a kind of diffuse noise model. And for the diffuse noise model, it's assumed that the energy of the noise all around every point is the same, or it's called the isotropic assumption. And that's why we can, independent of the covariance matrix of the signals in the microphone, we can just replace that with the covariance matrix of the noise, which is calculated in the microphones. So here we apply the covariance matrix of the noise. So in general, W Hermitian, the covariance matrix of the noise, replaced from the previous one, and W with respect to this condition, which is unbiasedness condition. So that's the MVUE problem. If you solve this problem using the Lagrange multiplier, you can easily find this W to be actually this value, which is that's the coherence function of the noise. And in general, put this W here, W Hermitian or transpose over the signal of the microphones, give you this estimation of the source. So simplifying that, you just replace this with the covariance matrix of the noise using the assumption of diffuseness. And the problem it actually changes to minimize this value over the W subject to this condition. This becomes your problem. And that's a convex problem. You can easily solve it with any convex solvers. Using the Lagrange multiplier, you will get the W. And that W is the super-directed W that you get. No matter what is written here, it will be the super-directive W, or the weight function, or the super-directed beamformer. For delay and sum beamformer, what we do is very simple. We just do the alignment and average over the signals of the microphones. So we know that, based on this assumption also, we know that there is a time delay for the signal coming from the source to the microphones. So assuming here this one is 1, but for the rest you have different tau values, depending on whether the signal comes earlier or later. So if you can align this, which we do it with this V, and average over all the signals, you're simply having an estimator that gets the average. And that's the story of delay and sum beamformer. So in delay and sum beamformer, we do the alignment, time alignment for different microphones based on the location we already have it. So here you need more alignment because the signal takes more time to get to the signal to the sensor XM. But for the first one, you don't need that much. You don't need it's normalized to 1. You do the alignment, so we have the tau I, we get the V, and that's exactly the one that you put it here and take the average over the entire microphones. So the delay on some beamformer is very simple, just compensating for that time delay and average over the signals. And it gives you, so this is the weight. And if you apply it here, it's just 1/n V Hermitian and the signals of the microphones. And that's the signal you estimate. So this is also applied to the noise, but we hope that the noise is more cancelled than the signal, and most part of the gain should belong to the source. I will put the MATLAB code, simple MATLAB code, and you will see that super directive performs much better than the delay on some beamformer. But in general, you should look at if you look at these beam patterns for different frequencies, for delay on some beamformer and super directive beamformer, for example, for the lower frequencies, you see that the delay on some beamformer has a very wide beam. It almost, it captures almost everywhere. Because it has no, it's not trying to minimize. Here you have a least square problem that you're solving. MVUE is a least square minimization problem. So you're solving a minimization problem. But for delay on some beamformer, there's no kind of minimization. It's just averaging the signals. So that's why here you have just much less gain for the lower frequencies, but the same for the super directive. You see that you're just pointing toward the source that you want. And when it goes for the high frequencies, it's getting much better for the delay on some beamformer, because we saw that already. High frequencies are more localized than the lower ones. So for the high frequencies, it's getting much better, but still super directive performs much better than that. So the patterns, always when you compare these two, for the super directive is more directed to the signal than for the delay on some beamformer. But on the other hand, when we go further in the frequency, so it's 2000 hertz or 60 hertz, if you go to the 8 kilohertz and higher frequencies, then there's a problem happens for the super directive mostly, and it later happens for the delay on some beamformer, which is called spatial aliasing. So the same as what aliasing you had in the sampling, here is also another view for the sampling, but that's the sampling in the space. In the sampling, the theory of sampling in DSP, you were sampling the data in different times. Here, you're sampling from the physical signal over the space. And for the higher frequencies, what happens to the wavelength? And the point is that when it's comparable to the distance of the microphones, then it might happen that the sample that you get is aliasing, has aliasing with the sample of even the microphone is farther from the previous one, for example, but the signal that they get is in the calculations, it's shown that they have the same signal. And that's why the data is actually encountering with the kind of aliasing. So for the high frequencies, still the problem of aliasing happens, and there are many methods people try to actually compensate for that aliasing, but still aliasing remains as an open